In this discussion, we're going to look at trends in the observed values of the radius of atoms and of ions, ionization energy, and electronegativity. In looking at the reasons behind the observed trends, there are two things that I want you to keep in mind. And both of these contribute to this thing called effective nuclear charge. Effective nuclear charge is the attraction or pull that is experienced by the electron from the positive charge of the nucleus. And there are two things that can affect this. One is going to be, like we see here, is the number of protons that are in the nucleus, and the other is the number of electrons that are in between this outermost electron and the protons in the nucleus. And these are our core electrons, and we're also going to refer to these in this context as shielding electrons, okay, because they are kind of shielding that outer electron from the positive attraction, or the attraction from the positive protons. Okay, and a quantitative measure of this is referred to as the Z effective, or Z with a subscript of EFF, and that is typically determined by the atomic number minus this screening constant, which is often close to the number of inner electrons or shielding electrons present. All right, the first thing we're going to talk about is the radius of the atom. And as we looked at before, there isn't really a defined outer edge to an atom. And so one of the ways that they determine a measure of an atomic radius is they look at the nuclei, okay, because we have a nice, dense, focused positive charge that can be measured. And so we can find the distance between two nuclei in a bonded molecule. And what they do basically is they look at the distance between the nuclei in a bonded molecule here. So here's our two atoms, the distance between the nuclei, and divide that in half, and that is what we refer to as a bonding atomic radius, or sometimes it's called a covalent radius. But that's one way that they have of measuring the radius of an atom, and that's kind of what we're generally going to use in this course. So let's see here. Here is a kind of a little bar graph, three-dimensional type, and it's showing you the trends. And as you can see, it's decreasing as we go across a row, and it increases as we go from top to bottom. All right, so let's look at the reasons behind this. As we go across a row, all right, what's happening? Well, as I go, say let's look at the second row. As I go across the second row, I have the electrons. Every time I go to the right, we're adding another electron. But remember, these are all going into the second energy level. So the distance from the nucleus is not really changing all that much. And so we're really not getting a lot of additional shielding. However, what else is happening as we move? As we go to the right, each time we're adding another proton to the nucleus. So we're increasing our nuclear charge there, okay, without really adding a whole lot to the shielding. And so that's why it says due to increasing effective nuclear charge, okay? So as we move across, the nucleus is able to pull the outer electrons tighter and tighter and tighter. So the radius gets smaller as we go across the row. As we go down a column, all right, every time we move down one, even though the number of protons in the nucleus has increased, we've also added another whole layer of electrons. Every time we go down a column, we're adding another energy level of electrons, and that's going to dominate the size of our atom. So atomic radius gets bigger as we add layers of electrons or shells of electrons. Okay, now what about ions? Well, here's kind of a depiction here, and it's showing the difference here. Like, for example, this would be a lithium, the radius of a lithium atom, and then lithium forms ions by losing an electron, and so you can see there it's getting smaller. Okay, whereas if we look over here, so, and this seems to be the trend as we go across, but now look here. Here we have our oxygen atom here, and as we form an ion, whereas oxygen forms a common ion by adding 2 electrons, and you see that it gets larger. And so let's take a look here. It's focusing just on here. These are all metals forming cations. Okay, and as you can see, as we form a cation, as we lose electrons, the ions get smaller. Okay, and this is comparing the neutral atom to its positive ion. Okay, and then conversely, anions, on the other hand, as we add electrons, we increase the radius. Okay, and also the thing to note here is, look, as if I'm comparing these ions down a group, okay, we see the typical trend that we expect in atomic radius. As I go down a group of ions, even comparing negative ions, they increase in size the same way that the neutral atoms do. Okay, there's that. Okay, another way that you'll be able to, or asked to, compare ionic radii is where you have combinations of positive and negative ions. And anytime you have a group of positive, negative ions, look to see if they are isoelectronic. Isoelectronic means they have the same number of electrons. Okay? If they have the same number of electrons, then remember it always feels the same way. So their arrangement of electrons is going to be the same, which means their number of shielding electrons are going to be the same. So what else is left to compare in this sort of a situation? The protons in the nucleus. Okay? So if they have the same number of electrons, then you're going to look at the number of protons. More protons is going to make the nucleus small, or the radius smaller. Okay? So in comparing isoelectronic ions, more protons means smaller radius.